go ahead and get started. Are you videotaping on behalf of all the people who are not here today?
No, that's Jenny, who is the one person who's not here today.
Okay. So you guys have your exam on Thursday. Obviously, many of you figured that out.
Step in the right direction.
What's that?
That's a step in the right direction.
Yeah. If you have any lingering questions on that, I addressed them before class, and then you can email me. I'm optimistic we might be able to finish homework number 5 material today. And that'll be good because after Thursday's exam, we won't meet again for a couple weeks. First, you guys have spring break, then Cesar Chavez Day the following week, and then the one Tuesday we would meet. I am not able to be here, so I'm going to post some kind of supplemental lecture to get you guys, to have you guys watch for that, for when we return, so we can kind of be a little further along. So keep an eye out for that. Check the WebAssign after the exam sometime, and you'll see it posted there. Okay, so let's jump right into it. We're talking about magnetic forces. And we found that if you have a magnetic field B and you release a charge from rest, or release it throwing it with or against the field line, we get absolutely no force whatsoever on it. It just continues according to Newton's first law, because we found that the necessary ingredient to feel a force from a magnetic field was a perpendicular component of the velocity. So you have to have motion that cuts across the field line, either in whole or in part, in order to feel a force. So here we have a charged particle which is cutting entirely across the field line. It's in fact perpendicular to the field line. And then here we have a charged particle which is thrown sort of across the field line. It has components to the velocity, both parallel and perpendicular. And it's really that perpendicular that's crucial. That's what causes there to be a force. The force direction is into the page. That's something called the right-hand rule, which I'll talk to you about today. The size of the force is given by this equation. So these two things collectively will produce the vector force. So size and direction. So as we noted at the end of last time, the force law is almost exactly identical to the electric force law, except for this extra ingredient, which is the perpendicular component of the velocity. Before we do anything else, let's go ahead and work out. This will actually give us the ability to get units of magnetic field. So we can solve here. The units of magnetic field must be units of force over units of charge and units of velocity. So we work it out. Force is in newtons, charge in coulombs. So far we have just newtons per coulomb, which is for electric field. But of course we have one more ingredient, meters per second. So the units of magnetic field are newtons per coulomb meters per second. Now that's kind of a mouthful, so we can't consolidate. One of the ways we can consolidate is we already have coulombs per second. We have an abbreviation for that. What's that? What's a coulomb per second? Amp, right? So if you wanted to say it a little bit faster, you could say Newton per amp meter. Or let's just come up with a unit for magnetic field. It's called Tesla. Okay. So magnetic field and SI units is measured in Tesla. Tesla, like the coulomb, is an unwieldy, large, non-everyday amount of magnetic field. For instance, you may know that an MRI machine generates a very large magnetic field. That's like 3 or 4 Teslas. Okay, far greater than anything you would encounter in most everyday situations. Okay, so let me first put a little practical thing onto the force formula, the size of it, and then we'll get to the right-hand rule. So first of all, I might label this angle theta, and then I could express v perpendicular as v cos theta. So that allows me to express the relevant component in terms of the entire speed and then cosine. Now anytime anyone tries to slip in a theta or a sine or cosine of theta into a formula permanently, you should of course be skeptical because one person's cosine is another person's sine, right? So anytime a cosine gets worked permanently into a formula, you had better believe there is a very specific way of identifying that theta, okay? So you might have asked, well, this velocity, couldn't I have broken it up like this, with this angle being phi, and then v perpendicular being v cosine phi? Oh, sorry, I put in the wrong thing. This is supposed to be sine. Excuse me, I was already thinking ahead, okay? So depending on which angle you use, it's a sine or a cosine. Now, of course, they come out to be the same thing. Theta and phi are complementary angles, as we say, right? They add to 90. And it turns out that cosine of theta, or sine of theta and cosine of phi are the same number. But how do you know when you're trying to use this form of the equation, how do you identify theta so that you're sure it's a sine? Well, there's a method for doing that. Theta is a special angle and phi is not. The reason why is because theta is actually the angle between the velocity vector and the magnetic field vector. So I might actually write this to clean this up. I'll put the sine of theta on the end because they're all multiplied. What does it matter? And that angle is very specifically picked as the angle between v and v. And if you pick the angle in that way, you don't have to worry if it's sine or cosine. It's always sine. Okay? So this is not the first time we have used the angle between two vectors. The most prominent example was from last semester when we were doing work. Right? Remember we had to identify the angle between the force and displacement vectors? So that's the same thing here. Let me just remind you that when you're talking about the angle between two vectors, you place them tail to tail. That's not to be confused with vector addition, which you place them head to tail. We're not adding these vectors. Even if you wanted to, you couldn't. You can't add a velocity to a magnetic field. That's like trying to add an apple to an orange. Okay? So we're talking about identifying the angle between the two vectors. The angle between two vectors can range from a minimum of 0 to a maximum of 180. 0 is when they're perfectly pointing the same way. 180 is when they're pointing opposite. And if you identify the angle in that way, it's always a sine in the equation. You don't have to worry about if it's a sine or not, it's always sine. So these are two different forms of the equation. They both have their strengths and weaknesses. This form that I just developed, it's nice because it's meant like kind of plug and chug, like, you know, set it and forget it kind of thing. You just put in everything. You put in the charge, how fast it's going, what field it's in, always sine, and then you put in the angle between the velocity and magnetic field vectors. I like this one, conceptually speaking, because it reminds you that the only way you're going to ever get a force is when you have v perpendicular. So you have to have some or all of the force perpendicular to the magnetic field line. So it's very conceptually nice, but the problem is that when you get down to calculating, v perpendicular would involve some SOHCAHTOA, and who wants to do that when we could just do it once and never have to do it again, okay? So this is more for calculations, and this is more for concepts, okay? All right, so that's the size of the magnetic force. Now let's go ahead and learn the right-hand rule. The right-hand rule is a mnemonic. I've counted at least 6 different versions of them. Okay, there's lots of different right-hand rules. I'm just going to show you one that I like. It's called the slap rule. You can use a different one if you like it. The basic thing is you have two vectors, you slap one into the other, and your thumb gives you the third. So in this case, what you do, with the palm of your right hand, to slap V into B. Your thumb gives the direction of the force. So here's what I've tried to do here. I have tried to construct this situation out of whatever these metal rods are. So I have the V vector here, there we can see. I have the magnetic field vector here, and then this will be the force. So what I do is I slap V into B, my thumb points like that, okay? So again, these two don't have to make a 90-degree angle to each other. That would be silly. You're entitled to throw a charge into the magnetic field however you want, okay? But the force will always be perpendicular to both of these. So basically you can think of it, if this is easier, V and B form a plane, and the force is always perpendicular to that plane. So again, try it again, slap V into B, that's the direction of the force, okay? So common mistakes, people do this, they do some kind of top karate chop thing, okay? So you gotta use your palm, okay? So not this, okay? No back slapping, okay? So not like this, okay? So that's one thing, because you notice that'll give you the exact opposite answer, right? I see this all the time where students are working, they're like, man, I'm going to be efficient. I'm going to work on my exam, and then I'm going to be doing my right hand roll at the same time, slap with the palm of the hand, and whoops, what's the problem? I'm using my left hand. It's called the right hand rule for a reason, okay? So notice that your hands give opposite answers. Slap something into something. Whether you're using your right hand or your left hand matters. So if you're right-handed, put the pencil down, use your right hand, pick the pencil up. This is one of the few times in life where left-handed people actually have an advantage, okay? To be writing with your left hand and doing the right hand rule with the other hand, okay? Okay, so that's what we're thinking of. Remember to visualize this. This is all you need to visualize, but you need to be able to visualize it in any orientation, okay? The key is that these two don't have to be perpendicular to each other, but the force is always perpendicular to both, okay? So let's go ahead and write that down. So these two don't not necessarily perpendicular. They could be, but they don't have to be. You're entitled to throw a charge into a magnetic field however you please. But the thumb, the force, is always perpendicular to both of those. Okay? So we'll do lots of practice today. Let's go ahead and start with these examples here that I posted, and I just told you the answer. Now we can see why that answer is true. So here's what we do. We take our right hand. First, make sure your fingers are pointed with V. So they got to be pointed up to the ceiling. Okay? Now you got to do the beauty queen handshake until you're ready to slap V into B with the palm of your hand. And I put my palm facing to the right because the magnetic field is over there. So like that. Okay? V into B. See that? So V into B. My thumb actually points into the page. That's how I do that. So that was a whole 90-degree slap because here the velocity happened to be perpendicular to the magnetic field, right? I had to go 90 degrees. Slap. 90-degree slap. This next one, slap isn't that long, right? I point my fingers along with V, and I do a nice little short slap, okay? V into B, my thumb is still into the page. And it's no surprise because the relevant part of the force, the perpendicular part, is identical, right? They both point like this. This V parallel doesn't really matter. It's like this. If you only had V parallel, you wouldn't feel force at all. So these both have identical pointing V perpendicular, so it's no wonder if they have the same V perpendicular direction in the same field, same force direction as well. Okay? So that's the right hand rule. We'll do it over and over and over again today. Let's start with an example where we can actually visualize what happens to this trajectory these are obviously problematic because the force is going to pull it into the board, into the next room behind the whiteboard, and we can't draw it anymore. So let me draw an orientation where we can actually see what's going on. And in order to do that, I want to draw the magnetic field itself as into the page. And let me not draw it everywhere, because that's just annoying, but you imagine a nice even spacing of magnetic field lines putting into the page everywhere. So, all right, fine, I'll draw a few more. Okay, so on and so forth, etc. All right? So, there's magnetic field. So, let's throw a charge in there. I guess let's throw it like this. We'll practice the right hand rule. Take out your right hand. The velocity points like this, and then I want to do the beauty queen handshake until your palm is oriented like this, because I want to slap it into B, which is into the page. So slap, and the force is left. Notice that the force came out perpendicular to both of the other two. It's definitely perpendicular to the velocity, and if I can draw the force at all in the plane of the page, and I can draw it on the whiteboard, it must be perpendicular to the magnetic field, because the magnetic field is perpendicular to the whole thing. So now we can actually chase what happens. This thing is not going to go straight. It's going to get nudged off to the left because of that leftward force. So let's do it again. Pick it up over here. So now the velocity is like that. Point your fingers to the left. Orient your palm such that you can slap B into B. B is into the page still, so B slapped into B, psh, force is down. Okay? You gotta do the sound effect or you don't get the right answer. Okay? So what you see is that the force is actually always going to stay perpendicular. So we saw forces like this in physics 1. We called them guiding forces. An example of a guiding force that we saw in physics 1 was the normal force in like roller coaster loop-de-loop problems, right? Remember that the normal force was always perpendicular to the motion, and what that meant is it does no work, which means that it can't change the kinetic energy of the object. The only reason why that roller coaster speeds up and slows down is because of what? Potential energy of what? Gravity, right? So basically gravity is the thing that's speeding this up and slowing this down. The normal force just guides it on this weird loop-de-loop path, but you are not going to be going any faster once you go around like this and achieve some final speed than if you fell off the side of the track, okay? The normal force has no say in going faster or slower. The normal force just has say in where you go. So it can't change the kinetic energy, so it has no effect on the speed. Hence we call it a guiding force. It can change the direction of motion, but it can't change the speed. So no effect on the speed, just the direction. That is also what we now have with the magnetic force. Or you can refer to the magnetic force as a guiding force, or you can refer to it as deflective only. So it can deflect the motion, and it clearly has curved it here, but it can't make it go faster or slower, so it's going to just be going the same speed, but in a different direction. The magnetic force can do no work. That means that if a charge has no kinetic energy, it's going to stay having no kinetic energy. It's going to stay at rest. The magnetic field cannot add kinetic energy. And if you are moving, then it doesn't make you go faster or slower, it just changes the direction of motion. Okay? So, let's keep going. This thing is not going to go straight. It's going to now have a deflective force downward. And you can probably see where I'm going with this. Make sure you can do the right-hand rules to show that this thing is going to bend in a circle. Okay? So we'll do do lots more right-hand rules later today, but make sure you can fill that out. Make sure you can get that the other two cardinal points of this thing, you could get that those forces look like that. In fact, what we're going to go ahead and do is say, hey, look, that's circular motion. So what the magnetic field has done is it has deflected the motion that you put the particle into the field with into a circle. We might as well go the extra full route and say the centripetal force needed to go in a circle is provided by the magnetic force. So we go ahead and put in our two equations, Q, V, B sine theta. And mv squared over r. Good old mv squared over r from physics 1. So first of all, what should we put in for the angle between the velocity vector and magnetic field? Is that a constant? The velocity certainly changes direction all the time. Does the angle between the velocity and magnetic field change? No. What is it all the time? 90. Because no matter how much the velocity swirls around in the plane of the page, it's still in the plane of the page. And the magnetic field is perpendicular to the whole thing. So sine of 90 is 1, which of course is the maximum value of sine. And the reason why is that this trajectory is maximally cutting across the field lines. There is no component of this velocity that is with or against the field. If that was the case, you'd have a part of the velocity going into the page or out of the page. Into the page would be with the field line a little bit. Out of the page would be against the field line a little bit, but we don't have that. We're basically in a situation like this. In fact, this right here, if you imagine, this is going to curve into the page. Well, then what? It's going to curve into the page and make a circle. We're just looking at this exact picture from the back, right, where I'm kind of standing right now. Right, so for me, I see the field line going away from me, and I see the thing going in a circle. That's what we're looking at here. Okay? We're just looking at the same situation from a different perspective. So let's solve. If you solve this, you can get the radius of the orbit. And this right here is definitely one of the most useful equations that is not available to you on the equation sheet. You're going to want to immediately be able to solve for this if you need it. I guess for the multiple choice questions on exam 2, you can memorize it. But really, it's not worth your brain capacity when you can just take this, which is on the equation sheet, set it equal to this, which is on the equation sheet, and a line later you have that. Okay? So this right here gives us the radius of the orbit. Let's take a look at the different factors which are in here. So if the mass is larger, then the radius of the orbit will be larger. That makes sense to me because mass is a measure of inertia, right? How stubborn something is to make a change. So if you have some big mass, it's not going to be as easy to take in a circle, and the circle is therefore going to be more gradual. So basically, more inertia and a more gradual turn. Okay? We can likewise make the charge bigger or make the magnetic field strength itself bigger, and those will actually both drive this thing into a smaller radius circle. So we can cause a tighter turn by increasing the amount of charge or increasing the amount of magnetic field. Now that makes sense because what you're doing with both of these are increasing the magnetic force. The magnetic force gets stronger when you have more charge and or a stronger field to pull on it. And so if you have more force hugging the turn, then of course you're going to be able to hug it into a tighter turn. Now the last one is more tricky. The speed, according to the equation, if you go faster, you go into a more gradual turn. Now that one's tricky because it seems to be at odds with what we just said about the charge and magnetic field. We said that if you make the charge or magnetic field bigger, it makes the force of magnetic force stronger. And we see it over here too, right? If you go faster, you should have more magnetic force. So why doesn't it then make a tighter turn? Well, here's the problem. If you double the speed, you will indeed have twice the magnetic force. You will have a larger force pulling on it. But over here, if you have twice the speed, guess what? You need 4 times the amount of force. So this is what you get, whereas the amount of force you need is proportional to v squared. So this is what you need. So yes, the force that you get is stronger, but the force you need is even more than that. So guess what happens then? You don't get to go in a tighter turn just because you have more force, because you need it even more than